Hello everyone. Let me introduce my name first. My name is Infantri Siahaan, and I am a mechanical engineering student in Udayana University. And now I want to presenting a topic that is cast irons. Okay, next. Here's the topic that we will discuss. This topic, and the main reference I take from this book, Metalurgi, Non-Metallurgist, second edition from Arthur C. Riordan. Okay. Cast iron, like steels, are iron carbon alloys. The difference is that cast iron typically possess higher carbon level than steels, so that cast iron can take advantage of eutectic solidification in the binary iron carbon system. The term eutectic is Greek for easy or well melting, and the eutectic point represents the composition on the phase diagram where the lowest melting temperature is achieved. Okay, the first topic is basic metallurgy of cast iron. Cast irons are heterogeneous multi-component ferrous alloys that solidify with a eutectic. For example, when an iron with 2.5% Celsius is cooled below the liquidus line, like in this picture, freezing begins first with the formation of austenite dendrites called pro-eutectic austenite. These dendrites grow and new dendrites form as the temperature drops through the freezing range, and the carbon content of the remaining liquid also increases. When the increasing carbon content and decreasing temperature reach eutectic values, eutectic solidification occurs at the eutectic temperature of 1154 degrees Celsius for graphite dashed line and 1148 for cementite solid line. White and gray cast iron are differentiated by their fracture surface appearance and the type of eutectic they form during solidification. Gray cast iron, which solidifies with an austenite graphite eutectic, has a gray fracture surface. This is because fractures occur along the graphite flakes. On the other hand, white cast iron solidifies with an austenite iron carbide eutectic, resulting in a white crystalline fracture surface due to fractures occurring along the brittle iron carbide plates. In some instances, a mixed structure known as mottled iron, containing both gray and white characteristics, may form. The stable austenite graphite eutectic and the metastable austenite eutectic is high with significant difference in mechanical properties, including strength, hardness, toughness, and ductility. Historically, cast iron were classified based on the fracture surface appearance, white iron with a white surface due to brittle iron carbide plates, and gray iron with a gray surface due to graphite flakes. Typical cast iron composition. A cast iron can have a composition that make it hypoeutectic or hypereutectic with regard to carbon. Matrix microstructure. In addition to the carbon-rich base, cast iron, like gray, nodular, compact, and malleable, have a matrix structure that may consist of ferrite, perlite, bainite, martensite, and austenite. These 5 basic matrix structures can be developed in any cast iron, although they are not necessarily always produced in typical commercial practice. In gray iron, the S-cast matrix is predominantly perlite that consists of alternate layers of ferrite and iron carbide. It is very strong and tough. The methods of heat treatment including like stress relieving, annealing, normalizing, hardening, and surface hardening. Yeah, we can see the explanation of each method in here. Next is gray cast iron. Gray cast iron is the most common form of cast iron and is characterized by a microstructure with flake or lamellar graphite embedded in a steel matrix. Gray irons comprise a range of hypoeutectic and hypereutectic composition. Many gray irons are hypoeutectic and their solidification behavior can be illustrated with the help of the simplified ternary eutectic diagram taken at 2% silicon, like in this picture. In a hypereutatic gray iron, graphite forms as the proeutatic phase. Graphite forms in the liquid iron independently of austenite and grows unensembled by other solid phase. These graphite flakes are entrapped in the structure as solidification progresses, either as characteristic long-strike flakes or in rapidly cooled section as lumpy flakes with a star-like distribution. Yeah, long-strike flakes like the picture in A picture and star-like distribution like in this B picture. Ductile iron, also known as nodular iron or spheroidal graphite iron, is very similar to gray iron in composition, but during solidification, the graphite nucleates as spherical particles in ductile iron rather than as flakes. Casting of ductile irons, second only to gray iron in the amount of casting produced, account for over a third of all castings, ferrous and non-ferrous. The desirable range of carbon and silicon in ductile iron is a tighter range than that of gray iron. Heat treatment varies according to the desired effect on properties. For example, and as such, ferritic microstructure can be annealed to produce a ferritic matrix with lower hardness. Some of the applications for austin-pierced ductile iron include like gears, wear-resistant parts, high fatigue strength application, high impact strength application, automotive crankshaft, chain sprocket, refrigeration compressor crankshafts, universal joints, chain links, and dolly wheels. Okay, the next is malleable iron. The history of malleable iron began in Europe. A French scientist and metallurgist named Prof. wrote the first detailed discussion about malleable iron castings between 1720 and 1722. In America, malleable iron was brought in by Seth Boyden. He was familiar with the white-hard malleable iron from Europe and saw that there could be a good market for this material. Malleable iron shares many properties with ductile iron, such as high ductility and toughness due to its nodular graphite and low carbon matrix. It is also highly resistant to corrosion, easy to machine, and has good magnetic properties, making it suitable for magnetic clutch and brakes. Additionally, malleable iron's strong fatigue strength and damping capacity make it ideal for long-lasting, heavily stressed components. Okay, compact graphite iron. Compact graphite iron are the newest member of the cast iron family to be developed as a distinct category. Compact or vermicular graphite irons have inadvertently been produced in the past as a result of insufficient magnesium or cerium levels in melts intended to produce spheroidal graphite ductile iron. However, it has only been since 1965 that compact iron has occupied its place in the cast iron family as a material with distinct properties requiring distinct manufacturing technologies. The application of compact graphite irons stem from their intermediate position between gray and ductile irons. Compared to flake graphite irons, compact graphite irons have certain advantages like higher tensile strength, much higher ductility and toughness, lower oxidation, and less section sensitivity for heavy section. The last is special cast irons. Special cast irons are typically high alloy irons, which can also be classified as either white or graphitic irons. In gray and ductile irons, small amounts of alloying elements such as chromium, molybdenum, or nickel are used primarily to achieve high strength or to ensure the attainment of a specified minimum strength in heavy sections. Otherwise, alloying elements are used almost exclusively to enhance resistance to abrasive wear or chemical corrosion, or to extend surface life at elevated temperatures. The oldest group of high alloy irons of industrial importance is the nickel-chromium white irons, or nickel hard irons, which have been produced since about the 1930s. They are very cost-effective materials for crushing and grinding. In this martensitic white irons, nickel is the primary alloying element because at level 3 to 5%, it is effective in suppressing the transformation of the austenitic matrix to pearlite, thus ensuring that a hard martensitic structure, usually containing significant amounts of retained austenite, will develop upon cooling in the mold. Chromium is included in these alloys at level from 1.4 to 4% to ensure the solidification of carbides, that is, to counteract the gravitizing effect of nickel. So that's the explain of special cast irons. This is the different family from usually cast irons, like we see in the this iron. Yeah, this is special cast iron. Okay, I think that's all I can presenting about this topic, cast irons, and I hope this topic can useful for all of you. Okay, for all of your attention, I say thank you very much.